the resistivity at any temperature T can be calculated from the resistivity at another temperature T0 from this equation. So rho equals rho 0 multiplied by 1 plus alpha by the change in temperature T minus T0. Alpha is called the temperature coefficient of resistivity. It is usually tabulated in standard physics textbooks. So from this equation for the resistivity, we can calculate the new value once the temperature changes. And from the change in rho, you can calculate the change in R, the resistance. So we can generate such an equation for the resistance, very much similar to this equation, because L and A will not change for the same conductor, has the same length L, the same cross-sectional area A, so it cancels out from both sides, and we have R equals R naught by 1 plus alpha multiplied by T minus T naught, the same form for the resistance as a function of temperature. So when current goes on in the light bulb, because of the resistance, which is like a friction in mechanics, resistance here, the electron collisions among themselves, this will increase the temperature. As the temperature increases, the resistance increases. As the resistance increases, the current decreases. This table, we list the resistivity for some common conductors. As I pointed earlier, it's the order of magnitude for conductors is 10 to the minus 8. For semiconductors like silicon and germanium, you have these numbers. For insulators, you have 10 to the 16, 10 to the 15. So you have this wide range of variations between good conductors and good insulators, and semiconductor is in between.